Hello and welcome again to my Physics Online video lecture series. Today's video I'm going to be talking about two types of potential energy that we commonly encounter in a Physics 1 course. One of them I've already kind of danced around a little bit, which is gravitational potential energy. Worth recalling at the start of this video, what is it that potential energy does for us as a practical definition? Potential energy is the potential for a conservative force to do work. In order to use potential energy, we must define a ground, which is where we say that the energy has a value of 0. And as a general kind of summing of these two, we can therefore say that the change in potential energy is equal to, in some sense, the negative of the work done, meaning as a force does work on an object with a system, we add potential energy, or we take potential energy away from that force, and as we do work against that force, then we're adding potential energy that is stored in the system in that way. So what we want to look at is two types for today. Maybe one other thing to recall. You can find the potential energy in work, so you can find work, ergo potential energy from graphs. And the way that you do that is to find the area under the force versus displacement curve. And that gives you work, and it can give you potential energy. So what we want to look at is two specific types of potential energy. The first one is gravity, and in this lecture I'm limiting myself only to gravity near the Earth's surface. Yes, you can do gravity from far away from the Earth, but in keeping with the fact that different textbooks have a different sort of sequencing of material, I haven't really, if you're watching these in the order they're intended, I haven't really yet covered gravitational force, Newton's law of universal gravitation. So that one has a force that is inversely proportional to the square of the distance between objects. I'm neglecting that one in today's video. We're just looking at force of gravity is m times g. And that means that if you were to make a plot that has on it gravity on one axis and displacement, specifically height, on the other axis, that your plot would basically just look like a flat horizontal line. And so if you were trying to find the area between, let's say, 0 height, wherever we've defined 0 is, and your actual height of your object, we could call that like maybe h0 for height of object, then this area, the potential energy, U, would look like m times g times h of object. This would be u of object. Okay, and that actually matches with the simple case of work being force times distance. It gets more complicated if what we want to look at is a spring. So you'll recall from my previous lecture about springs, I have here basically a little spring on a stand. You'll recall that the way that springs work is the more you stretch them, the more force they apply. And so right now I have like a little mass hanger, and if I add some weight to it, it stretches out by some amount. If I add a little more weight to it, these are, I believe, both like 5 grams. So add a little more weight to it, stretches a little bit farther, add a little bit more weight to it, stretches it just a little bit farther. And you could use like the little scale here to measure how far it stretches with each of these. It's not really the point of today's video, so I'm not going to do that very thoroughly here, but you can kind of see that it stretches equal amounts additionally for equal amounts of added weight. And that was Hooke's law. So Hooke's law basically says that the force applied by the spring should look like negative of some spring constant times however much the spring has stretched by. Since we've got it hooked up vertically, we can call that a delta y if you'd like. That means that if I was going to, again, make a plot for spring force versus displacement, so delta y here, force here, that rather than having a horizontal line, I now have more of a diagonal line. And again, I need not pay too much attention to the minus sign for the purposes of this plot. I just know that as I stretch the spring, I get a force that's applied in the opposite direction, and as I compress the spring, I get a force applied in the opposite direction. Now, if I wanted to figure out how much work is being done for a given value, we'll just call this y. This right here would be essentially k times y. And the area that I'm finding here is the area of a triangle. So this tells me that the potential energy should look like half of the base, that's y, times the height, ks times y. And so the potential energy for a spring should look like 1/2 ks times y squared, or delta y squared, whichever you'd like to call it. And this right here assumes an ideal spring. So this is an ideal spring. Now, a real spring often has an additional property. This spring's pretty close to ideal in this sense. But a lot of real springs are wound tightly enough that you can start adding weight and nothing happens to them. So some springs basically end up with an equation that says F spring is ks times y plus some initial internal tension. And that means that if I was going to go and plot the force versus displacement for those springs, rather than just having a straight line, I still have a straight line, but I have a straight line that now has an intercept. So this could be my delta y, we'll put a little delta here. This could be my force from the spring. And instead of starting down here, maybe I end up starting here, for example. And so my graph ends up looking like this. Now note that if I put less force on it, I end up with a bunch of different forces for which the length is 0. And what that basically is akin to is if I had a more tightly wound spring, there's some internal tension within this spring that's pulling it together. And so as I add force to it, I'm just kind of alleviating that internal tension. Okay, and so this is just alleviating internal tension. Kind of like if I was going to go lift a heavy object and I start to apply force to it, it doesn't lift up off the ground, but what has happened is I've reduced the normal force between the ground and the object. Here I'm kind of reducing the tension in the spring, and actually therefore the normal force between links of the spring. In any case, what that means is that if I'm trying to figure out what is the total work done or the total potential energy stored in this system, let's again say it's stretched by some amount y, this right here becomes ksy plus F internal tension. And this value right here would be my F internal tension. F internal tension. Essentially, the way that you could go about solving for this is you could split it up so that you have a rectangle here, whose area you can find, and then you have a triangle here, whose area you can find. And this is just going to be always a right triangle. So this right here would have a value of 1/2 times ks times y squared. Okay, so y is this distance, ks, this right here, this is your ks times y, And then this part right here would be your F internal tension. So you'd have a plus F0t times y. So all of this is now equal to your spring's potential energy. Okay, so that's two basic types of potential energy that we're likely to encounter in an introductory physics course. All right, so we should consider as an example this case in which you've got a mass that's hung on a spring and then sort of like grabbed and pulled down so that the spring has stretched a total of 10 centimeters. And what we want to know is if we take u equals 0 to be this case where the spring is not stretched at all, like this, then how much total potential energy is in the system? Not here when I've hung the mass from it, but here where it's been further pulled down beyond that point. Now this may seem like a fairly complicated problem. We are assuming, of course, an ideal spring. Essentially, if it is not stated otherwise, you can assume that the springs are ideal. So here's u equals 0. Here is the actual potential energy we're trying to figure out. And this distance, if we put it in here, this would be my delta y, which is also equal to the change in height. So in some sense we could say that delta y is the negative of this change in height. In other words, as I stretch the spring more, I'm adding potential energy to the spring, but I'm also removing gravitational potential energy from the system. So if I want to figure out my total potential energy, that should look like 1/2 of the spring times this delta y squared minus m times g times h, which again is delta y. Okay, so my potential energy for the system, if I go back here and look at what I've been given, this right here is delta y. Oh, sorry, I'm given an internal tension of 4 newtons, so I also need a plus internal force times delta y term here. This is my internal tension. This right here is K. U was 0 initially. This right here is mass, but we need to convert it over to kilograms, so that's 0.15 kilograms. This right here should be in meters, so it's 0.1 meters. So my total potential energy for the system is 1/2 times 80 newtons per meter times 0.1 meters squared minus 0.15 kilograms times 9.8 newtons per kilogram times 0.1 meters plus 4 newtons times 0.1 meters. And so we would need to then calculate all of this. And when you do all of that in the calculator, you get 0.293 joules relative to when this whole system is unstretched. And it's 0.293, it's positive. What that essentially means is that this will tend to compress upwards if released. And so that's it. That's your example for this video. And that's all that I'm going to do in today's video. So hopefully you've learned something from it, and thanks for watching.